This is how we defined it last time, and of course, for the complex conjugate field I said it is better to think of phi bar as something which has charge minus q. So, okay. So, the rule is that if a field or if a field psi of x, by that it could be a product of fields, it could be composite, it need not be, it could be phi square, phi cubed, okay, has charge p, then the covariant derivative d mu of psi, which is defined to be okay. So, we need to check if two things we need to check, we needed to verify, is it a derivation, is it a derivation, that is Leibniz rule, is it valid. Okay. So, I gave you couple of examples, hopefully you have checked out. So, the first ones said, for instance, was if you take psi to be phi square, according to this rule it should be equal to d mu minus I, and charge of phi square will be 2 q. If phi has charge q, it is 2 q. So, now let us see if Leibniz rule works. We haven't here, this is just using psi as a single object which has charge q. So, now we can Leibniz rule will tell you that d mu of phi square should be equal to d mu of phi times phi plus phi times d mu of phi. So, this is just the standard Leibniz rule, which we will now, but this is just our initial definition, we can just check that this has charge q. So, we will write d mu minus I q a mu phi, and let us put the other phi on this side, and it is not hard to see that this is 2 times that. Okay. But this is exactly equal to this. How do we see that? D mu, so 2 phi d mu phi is nothing but d mu of phi square, and this would be just minus 2 I q a mu of phi square. Okay. So, this is what this is, right. Okay. So, Leibniz rule is valid, but I said, like I pointed out, the following thing is that the covariant derivatives do not commute. So, that is the property which we give up by going to the covariant derivative. Okay. So, we have to check. So, let us instead of picking one of these things, I will just choose an arbitrary field psi with charge p and act on it with d mu and d psi and ask what you get. Okay. So, what I want to compute is the following object. Okay. So, the question is what should this be? Of course, there is one situation where it would be 0, that is when psi has charge 0, then it becomes the ordinary derivative and we expect things to commute. Okay. And the standard practice in this is not to go ahead and work this way. What you do is to just compute d mu d nu of psi. Okay. And we can do it in steps. First point is that by definition d mu of psi has the same charge as psi, because it does not mess up the property. Okay. So, we need to remember so in this case if psi has charge p, so they have charge plus p. Okay. So, let us write out what we would write here. So, we would write d mu plus rather minus I p a mu acting on d mu of psi, which d nu of psi, which again we know what it is acting on something which has charge p. Okay. This way of writing it is little bit dangerous in the following sense, there is some ambiguity, because this d mu could, I mean what I mean by this is this, think of this as an operator. So, it acts on everything to the right of it. So, this derivatives here will act on not just psi, but it will also act on the a nu. So, let us write out the various terms. This is one term, and then there is another term which goes with this. Okay, so, we are done with one set of terms. Now, let us look at the next term. So, here when d mu acts on it, you actually get several terms, you get two terms, one of which is minus I p d mu a nu of psi. Then let me write it below that, minus I p a nu d nu of psi, that is this term when this goes and acts on this. The next one would be when this acts on this, okay, and that is just minus minus will give you a minus p square a mu a nu psi. So, I have written out all the terms, there are 1, 2, 3, 4, 5 terms. Okay. But now, the key point is we just want to take the commutator. So, it is just simple to anti-symmetrize by seeing things and just look at terms which are symmetric and just throw them out. Okay. So, obvious symmetric terms, if I anti-symmetrize, this would go to 0, so would this. Okay. So, I do not need to worry about these two terms, it is just the other two terms I need to anti-symmetrize. So, I anti-symmetrize this guy. Okay. And then I also somewhere I have missed something here, this is okay. Okay. So, now even if you look at this, this is a symmetric combination of these two guys. This is just mu nu, exchange them with the same sign, both of them come with minus I p. So, let me, so all these things which I have underlined are 0. Here this by itself is 0, this by itself is 0, but this combination is 0, the sum of these guys. So, you can see that, so this implies has only one term which is this guy, and let me now explicitly expand it out. But what is this combination? We have seen this before, is F mu nu, it is the field strength, electromagnetic field strength. Okay. So, now we have something very nice, we understand the field strength as, so yeah. Field strength actually measures the non-commutativity is actually a very deep result. Okay. When we go to more complicated situations, which we will see in this course, when you go to the situations where the group now right now we started out with SO2, but we could have started out with any other group, but we will see that there is exactly this sort of a setup. Okay. And we will define a covariant derivative, we will find out the we will see something which comes out to be the object which measures the how non-commutative the covariant derivative is, and we will call that the field strength. Okay. And that will be the definition, and one nice thing is you can see it depends on the charge. So, you have to pull out the charge here. Similarly, in those cases we will find that it depends on what it acts on. So, here it remembers this P is something intrinsic not to the commutator. Oh, I forgot a psi out here. It is not intrinsic to this, but is actually a measure of this thing. So, this is independent. So, you have to separate these two things out, and so the object that you get here is what you would call, I mean there are i's and minus signs etc., that is not so important. I mean that you can always say that is your definition, but we will get a proper definition later. But this is the most important point, that you get the field strength in a natural fashion. Okay, is this clear? Yeah. Yeah. Okay. So yes. So but that's just yeah. So yeah, you can ask how does f mu nu transform under local SO2, which is the same as U1. If you write it in the complex basis, it is called U1 transformations. Okay. And again you know this, if a mu delta a mu is d mu lambda, then it is easy to see that delta f mu nu is 0. Okay. But this you know already from electromagnetism, but this is very special to the abelian, which is SO2, all group elements commute. Okay. Has to do with this, only for the abelian case this is true. Okay. But in the non-abelian case we will see that delta f is not 0, but it is the next best thing to not being 0, in the sense that it will transform nicely. Okay.
We just compare the charges on both sides of this.
Which one?
Du, the commutator du outside.
Yeah.
Transforms with the charge P, and so does the right hand side.
Yeah, but that yeah, how does that help? Ah, yeah, okay, yes, yeah, you are saying by yes, so yes, I agree. So the statement here is, we know that the left hand side transforms nicely. If psi has charge P, left hand side transforms like something which has charge P. Now look at the right hand side, psi already transforms like charge. So whatever it is multiplying, it should not transform. If it transforms, then it will change the charge or something. Okay. So it does not transform. Okay. But yeah, absolutely right, this can be used. Okay. I just have one comment. In fact, I claim that all of you have seen the covariant derivative before. Okay. The context is the coupling of the electron or whatever to a magnetic field. What was the Hamiltonian? We have it was in the one of our problem sets also. The Hamiltonian was P minus E, or let us write it, yeah, E A by C whole square upon 2 m. Okay. And in quantum mechanics you know that you replace. So when it is acting on this thing, this combination P minus E A over C, P would become the operator I h bar del minus, forget the C, let us put C equals to 1, okay, and even h bar equal to 1, so that we do not have any of these things, minus I h bar, right, this minus should be there, minus I del minus E A. If I pull out i's etc., I think it will look almost like that, up to some signs. No, this is, it is not exact, I mean I think there is a sign difference, but you can see that it depends on the charge. It's so in some sense this is the origin, if you wish. So in fact there was a question outside of class, people asking me, was this how things were discovered? I do not think so. I mean already in quantum mechanics we had seen things like this, and when you go to, first thing is you make the next step to relativistic quantum mechanics, there you replace this with the 4 vector kind of thing, and the A is already a 4 vector. So you can ask what P mu minus E A mu would look, and the derivative form, and then you would see naturally something like this. Okay. But there is something slightly different, I mean we are not yet there, this E out here is the electric charge, it is a coupling, while this q out here is just a number, it is an integer, because we said that it had to e power I q alpha. So, our q was necessarily an integer. So, there is a little bit of redefinition I need to do to bring e back into the story, okay. That I will do a little later, but right now what we should do is go back. So, now we have checked that the covariant derivative that we have defined has the properties, the promised properties, okay. So, now we have a nice Lagrangian density which is a function of phi and d mu of phi, and its complex conjugate, but I will not, I mean I will just write those things, which is invariant, okay. But actually this is a little bit of a fraud, it is fraudulent, because this has d mu as a field in the thing, in the story, and in principle you would like to say why not have a kinetic energy for that field, the gauge field, the vector field, why not add kinetic energy or even a potential energy for that, why not, okay. And there is no reason not to do that. So, you can write the analog of LEM of A, okay. I am using EM here to remind you, and so what would LEM be? It would be okay, and in my convention I will put an E out here. I am sorry, do I need an E here? No, yes, I need an E here. This is my E. This E is supposed to be the electric charge, okay, and Q just measures everything in terms of the electric charge, okay. In field theory, electric charge is a coupling constant, it is like m square lambda in the potential, these are like terms like that, it is similar to that, you get an E square, okay. So, this is what you write, and the key point is if you try to write a mass term, suppose we try to write a mass term, the natural mass term, you may think there is a sign error out here, there is not, it has to do with our sign convention, okay. And you would write a mass term, you might think I could write something like this, which is a mass term, but this is not invariant under gauge transformations or local SO2. So, this is not allowed by local SO2, which you also call gauge transformation. In fact, no potential is possible, okay. And we always restrict ourselves to two derivatives, there is not much, this is it, this is the only term you can write, it is unique, okay. If you permit higher derivatives, there are many more possibilities, etc., okay. So, you can see that in fact it is a very tight fit. If we are given, we started out with a system which was just a complex scalar field which had local SO2 invariance, global SO2 invariance. What we did is we said let us ask the following question, can we make it locally invariant? We found that yes, modulo adding this extra gauge field through the covariant derivative, but nothing tells you that that cannot have dynamics. So, you can put this whole thing. So, you end up with a nice system which has where you find that the interactions or the coupling between the phi and the gauge fields are fixed for you, you do not have freedom in that, okay. This is that is why it is called minimal. You could have done more exotic things, you could have you can do, but this is kind of the minimal thing that you can do to get a locally invariant starting with a global this thing. The amazing thing is that this kind of structure goes through for any group, any global symmetry you want. If you want to make it local, you can just go through this process, okay. So, now let us sort of play with this and go back and look at this particular Lagrangian and expand it and see what it contains. It is kind of fun. So, the matter part, so the Lagrangian for This is what you have. Okay. Now, it is invariant under this. So, what I want to do here is to write everything out and expand it as a power series in mu. So, there is one mu buried here, there is another mu here. So, there will be a piece which is independent of that, then there will be a piece linear in that, and there will be a piece quadratic in that. Okay. And the linear piece is the interesting one. So, we just expand, we write this out. Let me okay. So, first step is set 0 this thing. So, that is just L naught phi. The linear piece, there will be two pieces, one from this guy and the other from here. Okay. So, let us write that out. So, let me start picking out this guy plus okay. So, this is the linear piece, and then there is a quadratic piece which is just with this. So, minus okay. Now, I have a question for you. Have you seen this linear piece anywhere? Probability, but that we got also as another current for. So, you can see that this piece, if I write this thing as J mu, I write it as this, where J mu okay. This is what we got, I by 2 phi this thing, or if you write it, yeah, I wrote it in this fashion also. So, you get all these factors, everything will work out. Probably at that time I just said q would be 1, it should to match that thing, but that is not so, that is not a big deal. But this is something related to a comment I had made when we discussed the currents, is that you could always sort of act like the parameter was local, and then you would find it as the coefficient of what was going with d. So, how does this transform? D mu of alpha. Okay. So, I said that that was the term which would measure, okay, and this is true. So, you can take it as a general statement that always the linear coupling actually would be this way. In fact, there are I know of instances where this kind of, it is called another method. If you have some symmetry, you could actually start out which you want to make local. So, you start out with the global part, you write the linear piece, okay, and then of course, you need the next order piece you want to fix. So, now you go ahead do the variation of that thing, and then you will find that you need to add one more term. In this case, it would terminate here, but there are examples for which it does not terminate ever, it goes on to infinity, and you keep doing these things, and people have used I mean sort of very clever tricks. I have seen clever tricks in the literature to push things beyond when you have nonlinear completely, this is at least quadratic and it ends, okay, but you can have situations where it goes on, and you I mean if you want to get the full closure, you can prove the existence of closure maybe, but here it's you sort of find this other piece come out, okay. In fact, a lot of things about the SO2 case is really very simple. We will see later that there is not, in some instances there is not much of a distinction between infinitesimal and finite, we will see that, okay. So, that is one part of the story, and another thing which you can see observe out here is that this piece has a mu kind of piece, okay. And this of course it is multiplied by this phi square, and we know that this term, this is completely invariant under local gauge transformations, but just bear in mind that this is similar to this, except that is a phi square, okay. So, but this was not permitted because it violates what do you call gauge invariance, but we are able to generate something like this. So, now do we now you can see that suppose if you are in a situation where u of phi was such that the ground state, okay, had a spontaneous symmetry breaking. So, phi equal to a was some finite number was this thing, then you can see that I can get something which look like a square. So, the mass, so that it would start looking like this object, if this is a gauge field, this cannot have a mass, as we discussed there, but you can get something which looks like a mass, okay. And it appears, I mean, so this leads to what is called the Higgs mechanism, which we will discuss in another probably 10 minutes, but you can already see that structure out here. So, in this very simple example, okay, I resisted the temptation to call it by what people refer to it in the newspapers. So, I will not repeat it, but I am sure you know all heard about it. So, what it is called, but this is called. So, now let us just sort of before. So, this is the structure of the Lagrangian. Let us ask what the equations of motion look like. We can go back and ask what are the ground state, etc. We can ask these things, okay. So, equations of motion, okay. By the way, when we wrote Maxwell's equations, we wrote the equations of motion as something like this, right? D mu f mu nu equals to some up to I mean factors are not so important, was equal to j nu. In fact, in this if you write out the analogous Maxwell's equations for the gauge field, you will get exactly that, because it is the first variation, it is coupled to j mu. So, you can think of this as j mu, and you can see that you actually get the source part. So, from the viewpoint of the electromagnetic field or the gauge field, this is this coupling is just this is really like the current, okay. But you will get an extra, you will get one more piece out here, okay, and even that is interesting. So, I will just write out what I mean by that. I will write something co, okay, and what is that? So, that would be it should not matter, but okay. Yeah, where will slightly differ from this. So, let me just write that out. Okay. So, this if you look at this object does not transform nicely under local gauge transformations, but this does, okay, and this transforms like something which has charge 0, which okay. So, I do not need to do any deep thing to see how this will come and fix that. This is the power of what is called covariance, okay. So, what you do is you write things in terms of objects which transform nicely, and then proofs become much easier. So, the hard work goes in defining those things, and then you are done, okay. So, here you can get this. So, this is the equation of motion for a mu, okay. Now, I have to do the equation of motion for phi, and again I should tell you there is a nice method of doing this. You might think, oh, how do I do this? Should I go to reals and do the equation of motion for phi 1 and do the equation of motion for phi 2? The answer is no. What you do is you think of phi and phi bar as independent fields, okay. So, when you do the variation here, the delta, if I am doing a phi variation, I only vary this, but not this. I think of phi bar as independent of that, then all factors, everything will work out, okay. So, now let me just go ahead and write the equation So, let us write out the equation of I am just a little bit I want to check if okay. So, the equation of motion would be box of phi equal to minus u prime of phi. Now, I was worrying about a factor of 2, because when I do this variation I will get this is what it would have been in the absence of the gauge field. Okay. But now again yeah. Okay. I think now I am okay. So, the reason I was thinking a little bit is first thing is that if you see if I do a variation of phi, I get the equation of motion for phi bar, because that is what remains, number 1. And of course, here this you just do the derivative with respect to phi. So, that is what I have done, and the easy way to understand that this has to be correct is that phi in the denominator is like charge minus q. Okay. So, this is so now again the charges are fine. So, this has a nice transformation property. How do we make this correct? Just it is just the covariant. So, okay, covariance fixes it, but you do not have to believe me, and you should not believe me at least once in your life. You just go ahead and take these things and check that you get that. Okay. You will, I mean there is no doubt about it. So, this is the equation of motion. Okay. So, now we want to know again what is the ground state, etc., and of course, we need the Hamiltonian, as we will see in the next lecture, and some of you have already proved it in the assignment. You know that the Hamiltonian for just this part is just is some positive definite thing. It is E square plus B square, okay, with some halves or whatever, half E square plus B square in this setup with an E square in the denominator. It is anyway it is some positive definite thing. So, let us say that when mu was 0, when mu is 0, then we are back to the old classical vacuum, and what was it? You look for phi was equal to some constant, and it was the minimum of u. This is what we would have chosen. Okay. And so depending on this thing, so claim in the presence of A, the classical vacuum solution phi equal to exactly this constant and mu equal to 0, because what is that doing? Setting mu equal to 0 tells you that the energy density from the gauge field sector is 0, and this is the minimum of that. So, it is really you got the 0 thing, because the Hamiltonian density we will see will be a sum of positive terms, and I have achieved that. I can't go any more, any lower. This has 0 energy. Is this clear? Okay. So, whatever the hard work we did earlier, again minimal prescription or whatever is nice, it tells you that the classical vacuum that you had was the same, but actually there is something different now from the earlier thing, which is that so, and let's now look at the case when the constant is 0, when phi is equal to 0 is a vacuum. This is the case when you do not have spontaneous breaking of SO2. Okay. Phi not equal to 0, okay. But suppose phi is not equal to 0 is is the vacuum configuration. Then there is something very interesting that happens. I could write, I do not need to just write this, I could choose a new solution. So, let us say that phi equal to a mu is equal to 0, a is that constant, but I could write a gauge equivalent solution which is like this. Okay, because I have local gauge symmetry, this configuration is not different from this. They are physically equivalent configurations. In particular, suppose A is a complex constant. Okay, suppose A is complex. I mean, because the ground state would be mod phi square equal to A square, right. A is I mean, let us write it, no, let us write it as this, as A. Let me write it this way, so that then I do not need to, so that A is real. I will rewrite this, I think I should just rewrite it. So, that phi prime I could write that as some a e power I theta plus I q alpha okay. I have just written a gauge equivalent configuration. Now, we can go back and redo, we can redo our earlier analysis. Of fluctuations about this thing. Okay. So, now I could, what the way I would do that is by shifting the A. So, then you would write phi prime equal to A plus eta and e power I theta. So, first step is that you can see that if theta were some constant, I can always the phase of it I can eat it up by shifting alpha, and a mu will continue to remain 0. So, I can I mean I can keep making global transformations such that I reach phi prime equal to 0, I mean the phase becomes 0, but now when I am doing fluctuations I will write theta will be a function of x, but nevertheless I can still have this gauge degree of freedom. But of course, now alpha can be x dependent. So, now I can choose, rather can choose alpha of x q times alpha of x to be minus theta of x. So, I have much more degree of freedom, not just taking away a global phase, I can get rid of the phase permanently. Okay. But what happens is that because of that you will see that but the gauge field will remain, I mean it is just a picture of. So, in some sense you can see that the pure gauge part, it does not change, the field strength is still 0, the pure. So, this kind of thing terms are called pure gauge, it is just a gauge transformation, but that can be used to eat up the phase. So, they are equivalent to each other. Okay. So, the idea here is that I just get rid of it and always work with. So, when I look at the phi prime I just have the eta fluctuation which is one real scalar, that was the radial fluctuation. So, now coming back to this kind of term, so now this just becomes a plus eta square, and now you can expand it out and you get an a square a mu this thing. So, you find that you get a mass term in the presence of spontaneous symmetry breaking. Now, it is more precise than what I just said in words, you get a mass and you know what the mass is. Okay. And what happens to this term, you can convince yourself that this is only the phase part, it will disappear. Okay. So, there is only this piece to look at. because if you write phi as some if you write out phi as some radial part times e power I theta of x in general, you will find that this term is just d mu of theta, and but we have just set theta to 0 if you wish by our choice of gauge choice. So, this term vanishes, but this will remain, and we can expand this out and we get crucial thing we get. So, okay, a mu is not, by the way I should write out I will have to add fluctuations even for this, even this can, okay. So, this part will be there. So, you will get terms like this plus interactions, what I will call it. So, there will be a term which would look like eta a mu with some coefficient plus another coefficient eta square. Okay. So, these are, if you wish, this is cubic in the fields, this is quartic in the fields. Okay. So, if you look at the quadratic piece, which is this guy, you can see that there is a mass term, okay. So, it tells you that in this background the lower energy fluctuations of a photon is as if it has a mass. Okay. So, in other words, so if you have spontaneous symmetry breaking in the presence of a local gauge symmetry, the result is somewhat different. Originally what did we have? We had a massless fluctuation associated with this field theta of x, there was no this thing, but now what has happened, theta has disappeared, okay, and it shows up as a mass for the gauge field, which was not allowed, which is not possible. Okay. And the reason this has to happen is because if you have a massive photon, that should have, in other words, it should have a longitudinal mode. Longitudinal mode is roughly equal to one scalar particle, one scalar field kind of thing, while a real photon, massless photon, which we know in real life, has no longitudinal mode, it has only two transverse modes. If you pick a direction, it has two transverse modes. Similar to that, so the massive guy actually has three modes, two transverse and one longitudinal, and the statement people say is that the photon, by this, now I am using terminology, if you quantize the thing, the gauge fields excitations would be what we will call a photon. Photon picks up a mass or equivalently longitudinal mode by eating the Goldstone boson. This is what it's colloquially, this is what is said. Okay. And but it is a nice, I mean it is a graphic picture, but it captures exactly what, and the process of eating we have already done, we did it by doing this, okay, and you end up getting a mass. But remember, as Coleman emphasized, symmetry is not broken, it is just hidden, not just global, even in this case the local symmetry exists. So, in the presence of local symmetries, the Higgs particle, I mean you get a, you have you get a mass for the gauge field, and this is called the Higgs mechanism. Okay. And by the way, this is kind of exactly what happens in what are called type 2 superconductors. In superconductors you have you find that you have an expelling of flux. Flux cannot go through superconducting regions. So, what happens is that if you have flux trying to come out through the thing, what happens is that you will find regions which are normal, but then the part here regions which where it is not allowed, photons, I mean magnetic field is not allowed, that is related to this fact. The region, the superconducting phase actually corresponds to something of this kind. Okay. So, there you have a complex scalar field whose which, if you wish, is the, this is related to phi in that example is related to the density of Cooper pairs. Okay. So, you know that the superconducting state occurs when the density of Cooper pairs picks up a non-trivial wave or non-trivial expectation value. This is A kind of thing, that in this A would be the density. So, once you have something like that, then you end up in the superconducting phase. In the normal phase, okay, what you will find is analogous to this. And you may wonder, how can I do this in a single model? The answer is very, very simple. Suppose we did this. So, we are, let us go back to this one example. It appears that is the only one I know, but let us look at that in more detail. So, that was, okay, if you expand this out, let us look at the quadratic piece, that would be the cross term between these. So, that would be -2. So, it will be lambda -2 lambda a square mod phi square. Okay. So, it appears that this thing has a negative mass term, but this is related to, if you draw the picture, that the curvature is the wrong curvature. So, this has a this thing. Suppose we have a situation where mass square for some field has the following property, where T is some parameter. Okay. So, now you can see that if when that parameter T is greater than T c, what is happening? This has regular this thing. So, you are in a situation where the lowest energy configuration is when T equal to 0, rather when phi equal to 0, but if it goes the other way, when T is below T c, then you got a negative mass, then the phi fourth comes into play and you get this double humped kind of thing. So, you can see that if the mass square or the quadratic coupling varies from positive to negative sign as you change a parameter T, okay, then you can go from a situation. So, for T greater than T c it is this, for T less than T c it is this, and obviously what is T in the superconducting example? T would be the temperature. Okay. So, you can see that there is a physical example where indeed this sort of thing happens. Okay. So, I mean in principle one does not need evidence for the Higgs mechanism, it already exists. Okay. It is another thing that we need to find a Higgs particle, because that has to do with something else. Okay. It has to do with fundamental particle physics, but there is enough evidence of Higgs mechanism in condensed matter systems. Okay. So, so I do not think the LHC runs are going to actually be proof of this trivial I mean this thing. There is enough examples for that. Okay. But the question in that context is, what is the precise mechanism for giving masses to various particles, not just the bosons. Okay. There is much more detail in that thing. We will see those examples also, at least in this course, but this is really the world's simplest example. Okay. And this picture that I have drawn also is the way one gets around Derrick's theorem. What did Derrick's theorem tell you? You cannot find finite energy time independent solutions in say 2 + 1 dimensions. Okay. And but in the whole argument which we had there, it involved only scalar fields. Okay. But now, so for that is part 1, I mean it is not the whole thing. So, in this thing what we have done is we have already changed the setting. Okay. We have added gauge fields into the story, and then there was, if you remember, I told you there was this problem. I mean, what did we do? We said that if we when we have a kink kind of thing, we had two, I mean the boundary of space was just 2 points, but if you have a plane, the boundary of space is a circle, large infinite circle. So, now the thing is that if the phase is what we have seen here in the presence of local symmetry, gauge symmetry, it does not matter, the phase is not relevant, phase is not a gauge invariant thing. So, I can go around the circle, I can make its phase do weird things. So, somehow you find wriggling space and you can find time independent solutions. Okay. And so, and that again is what we will find is that every time we add one dimension, we will get some new feature. Okay. So, we will go in this course one step at a time. We will start we did 1 plus 1 dimensional finite energy solutions. The next thing we will do maybe in a lecture or two is to look at finite energy solutions in 2 plus 1 dimensions, and then we will go ahead and see things in 3 plus 1, and then maybe in 4. Okay. So, rather in 3 and then we will go to 4, okay, and the course will kind of end somewhere there. Okay. So, I am done for now. We will spend the next couple of lectures, we will spend some time looking at just the pure gauge field. We will understand certain aspects about the vector field. I mean, you have done the problem set. So, from my viewpoint it is just solving the problem set, but I will go into more details.